Welcome back to the deep dive.
Yeah.
Oh man, I am so ready for this one tonight. You know those chats you get into like really late at night where you start talking about, I don't know, dinner, and suddenly you're questioning everything. Like, what is reality? What is my cat actually thinking when it stares at the wall?
Yeah.
That's kind of the vibe tonight. We're diving deep, really deep, into how other animals perceive the world, how they see, how they hear, and honestly, just what kind of bizarre, brilliant stuff is going on in those little brains, or sometimes those massive brains, stuff we can barely, wrap our own heads around.
It really is an exploration that it genuinely changes how you see everything around you. Your backyard, the park, even just looking at your dog.
Totally.
We've spent, well, weeks wading through this huge pile of research. I mean, everything from evolutionary biology, the physics of light perception, you name it,
Yeah.
all the way to the latest studies in comparative cognition, looking at social behavior, intelligence.
Right.
And our mission here really is simple. We want to give you the shortcut. We've done the heavy lifting, boiled down all the jargon. Please do.
And pulled out the most surprising facts, those real aha moments. So you walk away feeling like, okay, whoa, without having to read, 20 textbooks. No info overload, just the good stuff.
Okay, I'm already hooked. And seriously, you got to stick around for this one because we are absolutely going to ruin your idea of color.
Yeah.
Like forever. We're going to get into the mantis shrimp, which is just, a total freak of nature, let's be honest, with its 16 color receptors. 16? It's unbelievable.
And then there's this almost heartbreakingly beautiful thing where an octopus literally wears its dreams on its skin. We'll get into that.
Oh, yeah, the dreaming octopus.
Plus, ravens that understand, like, value and waiting for a better reward.
Yeah.
Probably better than some people I know.
Huh. Probably true.
And how your dog isn't just hearing your baby talk, it's actually smelling your fear or your happiness, like the chemicals.
The chemo signals. It forces you, really, to step outside that very human-centric bubble we all live in. What we tend to call intelligence or, complex emotion, it's not just us. It's not some exclusive club.
Yeah.
It looks like it's more of a universal evolutionary toolkit for survival. And it just shows up in forms we often dismiss or just don't even notice.
Like what?
Like a tiny fish that can count or a bird that remembers human faces for generations. Their sensory worlds are just so alien compared to ours. Sometimes it feels like the only thing we share is, the planet itself.
I love that way of putting it. That's a really chill way to frame it. Okay, all right, grab your tea, your coffee, whatever keeps you cozy, settle in. Let's jump right into it. The great spectrum swap.
Yeah.
Peeling back the curtain on vision way, way beyond what we see. Okay, so sight, let's unpack this.
Right.
We humans, we tend to think we see, everything, the full picture, but actually, we're pretty limited.
Yeah, we really are. We're trichromatic, which sounds fancy, but all it means is we have 3 types of cone cells in our eyes.
Red, green, blue, red.
Exactly. Red, green, blue. They let us see millions of different hues, which, okay, sounds impressive.
Wait.
But in the grand scheme of the animal kingdom, it's kind of average.
Average. I feel so basic now.
Well, our setup, trichromacy, it's basically built for, the savanna.
Spotting fruit and stuff.
Exactly, spotting ripe red berries or fruits against all that green foliage. That was the evolutionary pressure that shaped our specific color palette. But loads of other animals, our neighbors, they either traded that kind of color detail for better sensitivity in dim light.
Okay.
So they live in more of a muted pastel world. Or they crank the dial the other way into this hyper-vivid reality we can barely comprehend.
All right, let's start with the muted side then. The dichromatic neighbors. And this includes, like, our actual neighbors, dogs and cats.
Yep, our furry friends. They only have 2 types of cones, which means their world is primarily built around yellows and blues, stretching maybe a little into the ultraviolet, which we can't see at all.
So not black and white, like people used to think.
Definitely not black and white. That's a myth. But it is a much softer palette. Blues, yellows, grays. The really crucial thing, though, is they have major red-green confusion.
Ah, okay, so this explains.
This explains everything for dog owners. That bright red squeaky ball you threw onto the nice green lawn.
Yeah, my dog loses it every single time.
To your dog, that red ball is basically a blob of grayish brown that just disappears into the green background. It has almost no contrast for him.
No way. All this time, I thought my golden retriever was just being lazy or, like, defiant when he couldn't find the obvious red toy. He literally couldn't see it properly.
He literally couldn't. It's a genuine aha moment, isn't it? Changes how you play fetch.
Completely. So what are their main visual cues, then, if not bright colors?
Contrast, brightness, and especially movement, that's what catches their eye, not so much the saturation of the color. Our reading confirms cats are pretty similar, though they lean even more heavily on sensitivity and low light.
Right, cats are night ninjas.
Totally. They make up for the lack of color detail with way more rods. Those are the light-sensitive cells for dim light, and of course, those incredible ears that swivel around to pinpoint tiny sounds. But yeah, visually, definitely a pastel world for them.
And does that low light thing carry over to, like, the big cats?
Yeah.
Tigers, wolves?
Oh, absolutely. Same deal. They're also dichromatic, seeing mostly yellows and blues, but for them, the evolutionary driver wasn't spotting fruit in daylight, it was pure detection in the dark, night hunting.
So they need killer night vision.
Exactly. Precision vision at night is everything. Their retinas are just packed, absolutely loaded with rods. And that's why you get that eerie, kind of beautiful eye shine when a light hits their eyes at night.
Right, the spooky glow. What actually is that? You mentioned it earlier, the tapetum lucidum.
Yeah, the tapetum lucidum. It sounds technical, but it's actually a pretty genius bit of natural engineering. It's basically a mirror.
A mirror inside their eye.
Yeah, a reflective layer right behind the retina. So when light comes into the eye and passes through the rods without hitting one, the tapetum lucidum bounces that light right back through the rods again, gives them a second chance to catch that photon.
Whoa. Like recycling light.
Exactly. It's an efficiency hack. It means almost no light gets wasted. It boosts their night vision sensitivity like 6 times better than ours. It's a huge part of why they're such successful hunters after dark.
6 times better. Okay, that's both terrifying and amazing.
Okay.
So that's the muted world. Now, let's flip it. The creatures that went all in on color. The hyper-vivid world.
Right. Now we're talking tetrachromacy and sometimes even beyond that. Lots of birds, insects. They often have 4 types of cone cells, not just red, green, blue, but also one dedicated to ultraviolet light, UV.
UV, which is totally invisible to us.
Completely invisible. This just opens up a whole different reality for them.
Like pigeons, you mentioned them, they're tetrachromatic.
Technically, yeah. Pigeons see millions more colors than we do, and our research strongly suggests that this UV ability is super important for them. For navigation, maybe spotting subtle landmarks, finding food.
But it's more than just seeing more colors, right? It's used for communication, too.
Oh, massively. You look at a lot of birds, what seems like maybe dull brown or plain white feathers to us, they might actually be blazing with these intricate UV patterns that only other birds can see.
Seriously?
Yeah, crucial for things like courtship displays showing off how fit you are, for marking territory, even for telling their own eggs apart from, say, a cuckoo's egg that snuck into the nest, because the parasite's egg won't have the right UV signature.
That's amazing. So a bird we think looks boring might be flashing like a neon sign to another bird. Okay, and the classic UV master has to be the bee, right?
Bees are the perfect example. They actually can't see red. It looks black to them.
Oh, interesting.
But they are absolute experts at seeing UV. So a flower that looks plain yellow or white to us, to a bee, it's often covered in these complex blazing UV patterns, sometimes like a bullseye. They're called nectoguides.
Nectar guides, like runway lights pointing to the good stuff.
Exactly. A literal roadmap saying, pollen this way. That's only visible to them. It's incredibly efficient.
Yeah. And didn't you mention something about their processing speed? That sounded kind of trippy.
Oh, the speed is ridiculous. Honeybees process color about 5 times faster than we do.
5 times? What does that even mean?
It's about their flicker fusion rate. That's the speed at which a flickering light starts to look like a steady, continuous light to an observer. For us, it's around 60 times per second, 60 hertz. For a bee, it's closer to 300 hertz.
Oh.
So a light source that looks perfectly steady to us might still look like a distinct series of flashes to a bee. They're essentially experiencing the visual world in, like, fast forward compared to us.
That helps them navigate while flying super fast.
Exactly. Helps them track flowers, avoid obstacles, all while zipping around. It's incredible optimization.
Fast forward vision, UV roadmaps.
Yeah.
And then you get to the mantis shrimp. This is the one that just breaks the whole system. 16 color receptors.
16.
Our brains just short circuit trying to imagine that.
They really do. We genuinely cannot comprehend what that's like. They see UV, they see infrared, and they see different kinds of polarized light in ways we absolutely cannot.
So we have 3 color channels. They have 16. It just sounds like sensory overload. How does their brain even handle that?
That's the big question, and it's where the research gets really interesting. The current thinking, the main hypothesis, isn't that the mantis shrimp is seeing this super-duper high-resolution 16-color image all the time.
Oh.
Instead, it seems more likely they're using those 16 channels for extremely rapid, highly specialized scanning, like quick checks for very specific signals.
Okay, so maybe less like seeing a masterpiece painting and more like having 16 different warning lights for specific things.
That's a great way to put it, yeah.
Well,
It might be a much simpler cognitive task than the complex color mixing our brains do. They use polarized light signals, for example, to communicate super quickly with rivals or potential mates, or to spot the almost invisible shimmer of translucent prey against the water. It's like a hyper-specialized toolkit built for speed and efficiency in their environment. Not necessarily about appreciating a richer rainbow, but about seeing the threat or the meal or the mate instantly.
instant detection.
Yeah.
Got it. That makes more sense than just sensory chaos. Okay, and speaking of seeing underwater, what about sharks and the general rules for aquatic vision?
Well, one thing our reading highlighted is that land animals generally tend to see more colors than animals living underwater. And there's a simple physics reason for that.
Which is?
Red light gets absorbed really, really quickly by water. It just doesn't penetrate very deep.
Ah, okay, so the underwater world is naturally more blue and green.
Exactly. So evolution in aquatic animals tends to favor sensitivity to blues and greens. The opsins, those are the light-sensitive pigments in the cone cells, are tuned for that blue-shifted world. Sharks, for instance, are usually dichromatic, seeing mainly greens and blues. But where they really excel is sensitivity, using that tapetum lucidum layer we talked about.
Right, the light recycling mirror,
Yeah.
which gives them, what, 10 times better sensitivity than us?
Something like that, yeah. Lets them see maybe 30, 50 feet in murky, low-light water where we'd be effectively blind. They trade color richness for sheer sensitivity in their dim habitat.
Makes sense. Now, contrast that with some of the really weird land-based vision quirks, like the gecko.
The gecko is wild because it flicks the script on nocturnal vision. Usually, night animals sacrifice color for sensitivity, lots of rods, maybe only one cone type. But the gecko, it has incredible color vision at night,
How good.
like 350 times more sensitive to color in dim light than humans are. They're seeing vibrant, saturated colors when it's almost pitch black to us.
Wow.
It's thought that their cone cells, which are usually only for bright light, are just enormous and incredibly efficient at gathering every available photon. They can actually process color information even when light levels are super low, gives them a massive edge-spotting, camouflaged insects in the dark.
Mind blown. Okay. And my personal favorite seasonal adaptation, reindeer eyes changing color. This is genuinely bonkers.
It is absolutely bonkers. Their eyes literally change color with the seasons to cope with the Arctic darkness. In the summer, when there's plenty of light, the tapetum lucidum behind the retina is gold.
Okay, normal enough.
But in the winter, during the polar night when it's dark almost 24/7, that tapetum shifts to a deep, deep blue.
Why blue? What's the advantage there?
That blue shift changes how light scatters inside the eye, and it makes their retina something like 1,000 times more sensitive in those incredibly dim conditions. But here's the really clever bit.
Go on.
That blue shift also allows them to see UV light much better. And UV light reflects really strongly off snow.
Okay.
So, lichen, which is their main food source in winter, absorbs UV light. So against the bright UV reflecting snow, the lichen patches appear dark, almost black, making them super easy to spot.
No way. They have built-in UV goggles for finding dinner.
Exactly. And it probably helps them spot predators like wolves, too, whose fur might absorb UV differently than the snow. It's this incredible, natural, seasonal adaptation. Built-in snow goggles.
That is next-level evolution.
Yeah.
Okay, if sight is this weird and varied, I can only imagine what's going on with hearing.
Right, so hearing. Let's start with our baseline again. Humans, we generally hear sounds from about 20 hertz. That's a really low rumble, like distant thunder, up to about 20,000 hertz or 20 kilohertz, which is a very high-pitched whine.
And our sweet spot is around speech frequencies, right?
Exactly, around 3 kilohertz. That's where our hearing is most sensitive. But just like with vision, we are completely deaf to a massive range of sounds happening all around us, way above and way below what we can perceive.
Okay, let's go high first, the ultrasound stuff. Bots are the obvious poster child here, yeah.
Bats are famous for it. They can hear frequencies up to like 200 kilohertz. They use this for echolocation, sending out these high-pitched clicks and then listening to the echoes bouncing back to map their surroundings in complete darkness. They build a 3D sound map.
Down to incredible precision, right?
Oh, yeah. Millimeter precision.
Mhm.
But our reading pointed out something cool. It's not just about the ears. They also have these tiny, super specialized hairs on their wings.
Wing hairs. For hearing.
Kind of. They sense tiny disturbances in the air currents right near their wings. This helps them make those final micro adjustments to snatch an insect right out of the air. It complements the sonar, giving them that extra layer of close range info.
So they're feeling the air turbulence around the bug as they close in. That's wild. But the bat isn't actually the champion of high-frequency hearing, is it?
Nope. Bizarrely, the title holder is a prey animal, the greater wax moth.
A moth.
Like,
Seriously.
seriously, this little moth can hear frequencies way up to 300 kilohertz, which is insane.
Why? What's it listening for?
Bats. It's purely a defense mechanism. This is like the ultimate evolutionary arms race fought with sound waves.
Counter-echolocation.
Exactly. The moth hears the bat's echolocation, even clicks at frequencies higher than the bat itself uses for hunting, and that triggers an immediate, panicked, evasive dive, a corkscrew maneuver to try and escape being eaten.
Wow. Think about the evolutionary pressure there. Developing the ability to hear sounds you never even make, just purely to survive your main predator. That's amazing.
It's a beautiful example of how specific threats shape sensory limits.
And closer to home, our own cats and dogs are hearing stuff way outside our range too, right? Up to like 60 or even 77 kilohertz.
Yep, way higher than us. And that's why those super mobile ears are so important for them.
The little radar dishes?
Pretty much. A cat has something like 32 muscles controlling each ear. A dog has around 18. They can pivot them independently, almost 180 degrees, to pinpoint exactly where that high-frequency sound is coming from.
Like a tiny mouse rustling in the wall.
Exactly. That high-pitched squeak or rustle, which might be just background noise to us, is highly directional for them. They get an instant, accurate lock on the location thanks to those swiveling ears. Our fixed ears just can't compete.
Okay, so that's the high end. Let's swing way down low now.
Yeah.
The infrasound giants. The ones dealing in those deep rumbles we might feel more than hear.
Elephant is the prime example here. They can hear sounds down to around 17 hertz. That's true infrasound.
And they use it to communicate over huge distances.
Miles, yeah. They produce these low-frequency rumbles, but here's the really critical part our reading emphasized. They don't just use their enormous ears. They use their feet.
Their feet, you mean they're feeling vibrations?
They're using the Earth itself as a giant telephone wire. They detect seismic sound waves, the rumbles traveling through the ground, using these specialized fatty pads on the soles of their feet.
No way.
And those vibrations travel up their leg bones directly to their inner ear. So they're not just hearing calls from 6 miles away, they are literally feeling the conversation ripple across the landscape.
That is profound. The
Yeah.
Earth as their communication network.
Wow, it allows for incredible herd coordination, finding mates, sending alarm calls, even through dense jungle where line of sight is impossible.
Okay, who else is down in the low frequencies? The pigeon came up again?
Yeah, the humble pigeon turns out to be an infrasound superstar. They can detect incredibly low frequencies down to maybe 0.05 hertz.
0.05 hertz. What does that even sound like
Oh.
or feel like?
It's hard to imagine. Think of a really, really slow, massive pressure wave, like the rise and fall of a huge ocean swell, or the distant churning of a massive storm system hundreds of miles away.
So, their famous homing ability, it might not just be about magnetic fields, it's also about sound.
It seems to be a big part of it. They might be using infrasound to build a kind of sonic map, detecting the subtle pressure differences created by distant mountains or coastlines or approaching weather fronts. It gives them another layer for navigation, an internal compass linked to sound.
Sonic compass, that's cool.
Okay,
Underwater, low frequencies.
humpback whales.
Humpbacks are the masters there. They hear down to about 15 hertz. And they need that low frequency because sound, especially low frequency sound, travels much, much further underwater than in air.
How do they hear it? Do they have big ears?
Not really external ears like we think of them. They primarily use bone conduction. Their massive skulls, especially their jawbones, act like giant receivers. Sound vibrations in the water travel through the jawbone directly to the inner ear structure.
So their head is the antenna, pretty much. And this allows those incredibly complex, haunting whale songs to travel for maybe 20 kilometers, over 12 miles, underwater, connecting individuals across vast stretches of ocean for mating, for social calls. The scale is just staggering.
It's kind of mind-blowing to think that right now, wherever you are, the air and the earth and the water are probably just thrumming with sounds. High-frequency back clicks, low-frequency whale songs, and we're just completely oblivious.
Totally deaf to most of it. And then, just to make things even weirder, you get the creatures that hear with body parts that definitely aren't ears.
Ah, yes, the non-ear hearing section. This is where evolution just seems to get creative.
We're just plain weird. Insects are great examples. Cicadas, they basically hear with organs in their stomach area.
Stomach ears.
Okay.
And crickets and katydids use their knees.
Well, technically, they have tympanal organs on their front legs near the knee joint. They look like little slits, and they're often tuned very specifically to the frequency of their own species' mating call.
So they filter out all the other noise.
Exactly. It's like having noise-canceling headphones that only let through the sound that matters most for finding a mate. Super efficient.
And snakes. They don't have external ears at all, right? How do they sense stuff?
Mostly vibration. They feel vibrations through the ground directly through their skin and their skeleton, especially the jawbone resting on the ground. Lets them detect footsteps of prey or predators.
What about their tongue flicking? Is that just for smell?
Smell and taste, yes, but possibly also for gathering airborne vibrations or chemical cues, which are then processed by a special organ, the Jacobson's organ, in the roof of their mouth. Their whole body is basically a low-frequency vibration detector.
Okay. And dolphins again. Showing up with another weird hearing adaptation.
Yep. For their sophisticated echolocation, they pretty much bypass external ears altogether. They receive the returning high-frequency clicks mainly through their lower jaw.
Through their jawbone. Like the whales.
Sort of, yeah. There are these channels filled with a special type of fat in their lower jaw, sometimes called the acoustic window. This fat conducts sound incredibly well. The jaw acts like a big antenna or receiver dish, funneling the sound pulses directly to the inner ear.
And it's super precise, right?
Incredibly precise, they can tell the size, shape, density, and even the material of an object just from the echoes. They can even supposedly detect pregnancy in another dolphin or a human by analyzing the echoes bouncing off the fetus.
Detect pregnancy with sound waves through their jaw.
Oh, okay.
That completely reframes the whole idea of listening, doesn't it? It's not just about ear flapping.
Not at all. It's about conduction, location, specialization. Evolution finds all sorts of ways to get the job done.
All right, we've spent a lot of time on the invisible worlds of sound and color. Let's get visual again, but this time looking at the anatomical hardware itself. Some of the physical designs that are just flat out weird.
Yeah, evolution definitely has moments where it seems to just go for maximum visual impact or solve problems in really bizarre ways. Welcome to the gallery of horrors, or maybe wonders.
Let's start with just eyes. Lots of eyes. More than the usual two.
Right. If 2 eyes feel standard, well, meet the scorpion. They can have up to 12 eyes scattered around.
12. What do they do with 12 eyes?
It varies. Some are simple light sensors, others might form basic images, helps them detect movement from multiple angles. And then there's the box jellyfish, which takes it even further with 24 eyes.
24 eyes on a jellyfish. Does it even have a brain?
Not a centralized one like ours, but it has clusters of nerves. And most of those 24 eyes are simple pits that just detect light intensity. But 4 of them are actually quite complex, capable of forming images. They help it navigate around obstacles and stay oriented, maybe even spot prey.
Still, 24 eyes. That's intense. Okay, what about size extremes? Biggest eyes.
That prize goes to the colossal squid. Their eyes can be up to 27 centimeters across. That's bigger than a dinner plate.
Dinner plates. Why so huge?
They live in the deep, deep ocean, pitch black, thousands of feet down. They need those enormous lenses to gather every single stray photon of light, probably to spot the faint bioluminescence of their prey, or maybe even the silhouette of their main predator, the sperm whale, looming above them.
Okay, that's deep sea specialization. Now contrast that with the ostrich.
Well,
This fact always gets me. The ostrich's eye is literally bigger than its brain.
it really puts things in perspective, doesn't it? It highlights that trade-off between sensory input and cognitive processing. The ostrich eye is a massive, highly specialized surveillance tool.
Built for spotting lions miles away on the savannah.
Exactly. Huge field of view, amazing distance vision, constantly scanning for danger. The brain's job is comparatively simple. See danger, run, see food, eat. It's all about maximizing that early warning system.
Okay, speaking of specialized eyes, the owl. Famous for
Yeah.
that head swivel, right?
Yeah.
Almost 360 degrees.
And that swivel is absolutely necessary because their eyeballs aren't spheres like ours that can roll around. They're more like fixed tubes packed into the skull.
Fixed. So they can't move their eyes side to side.
Nope. They have to move their entire head. But the upside is those tubular eyes are incredibly good at gathering light for night vision. And our reading threw in a fun fact. Owls are also one of the few birds that can actually see the color blue quite well.
Huh. Didn't know that. Okay, for sheer speed and coverage, you've got the dragonfly. This is like high definition, high frame rate vision.
Oh, yeah. Compound eyes with up to 30,000 individual lenses, or ommatidia.
30,000
It
lenses.
gives them nearly a 360-degree view of the world and allows them to detect movement incredibly fast. Their flicker fusion rate is way higher than ours. They basically see the world in slow motion compared to us.
Which is why they're impossible to swat.
Exactly. They see your hand coming from a mile away in slow-mo. Makes them amazing aerial hunters, too. They're flying around experiencing life at like 250 frames per second.
Okay, now for the master of multitasking vision, the chameleon.
The chameleon is just fantastic. Its eyes move completely independently.
The turret eyes.
Right. One eye can be looking forward, the other looking back or up or down. Gives them a full 360-degree scan of their surroundings simultaneously. True monocular vision.
But then they switch, right, for hunting.
Yep. The moment they spot prey, boom, both eyes lock onto the target, switching instantly to binocular vision. This gives them incredibly precise depth perception right before they fire that super long, sticky tongue. And remember, they're also seeing in tetrachromatic color, including UV, so they're spotting insects we'd totally miss.
That's some serious targeting hardware. And evolution even found a way to see above and below water at the same time. The four-eyed fish.
Yeah, the anapleps fish. It has this amazing split cornea and lens. The top half is adapted for seeing in air, the bottom half for seeing underwater. It swims along the surface, literally keeping an eye on both worlds at once. A natural bifocal.
Genius. Oh, and for just sheer protection in harsh environments. The camel.
Camels deal with sandstorms, intense sun. They need serious eye protection.
3 eyelets, right?
3. They have the normal upper and lower lids, plus a third inner eyelid called the nictitating membrane. It's thin, translucent, and sweeps across the eye horizontally like a windshield wiper.
What does it do?
It wipes away sand and dust, protects against wind, and even filters out some of the harsh UV glare, all without completely blocking their vision. It's a perfect adaptation for desert life.
Nature's built-in sunglasses and wipers. Okay, let's circle back quickly to that eye-to-brain size thing. We had the ostrich with eyes bigger than its brain. What's the other extreme?
That would be the tarsier. It's a tiny nocturnal primate found in Southeast Asia, and its eyes are enormous relative to its head. Each eye is about as large as its entire brain.
As big as its brain. Wow. Are they fixed too, like the owls?
Yep, fixed in their sockets. They're basically giant light-gathering buckets packed with rods, allowing them to see incredibly well in near-total darkness to hunt insects. They sacrifice eye movement for maximum light sensitivity, another extreme trade-off.
A masterclass in low-light vision, okay, and related to keeping those precious eyes safe or functional. The unblinking stare or weird blinking.
Well, snakes technically don't blink because they don't have movable eyelids. They have a fixed, transparent scale over the eye called a spectaculum. Constant protection.
So they're always staring. Creepy. What about animals that do blink, but weirdly?
Hamsters. Our reading mentioned that hamsters often blink one eye at a time.
Unilateral blinking. Why?
Vigilance. If you blink both eyes at once, even for a split second, you're momentarily blind. For a small prey animal, that can be fatal. Blinking one eye at a time means you always have at least one eye open, scanning for danger. Constant low-level awareness.
That's some serious dedication to not getting eaten. And the ultimate example of that vigilance has to be the dolphin, right? Sleeping with one eye open.
Unihemispheric sleep. It's incredible. Half of the dolphin's brain goes to sleep while the other half stays awake and alert. The eye connected to the sleeping hemisphere closes, while the eye connected to the awake hemisphere stays open, scanning the water.
Why do they do that?
2 main reasons. Constantly watching for predators in the open ocean, and also needing to consciously control the breathing. They have to surface for air. The awake hemisphere handles that. It's basically 257 vigilance, even while resting.
Okay, hold up for just a second there, because that dolphin fact, sleeping with half a brain and one eye open, that is just wild. Constant vigilance. Look, if you're enjoying this deep dive, if this kind of late-night weirdness and brain-stretching info is your thing, could you do us a huge favor? Please, like this video and subscribe to our YouTube channel. We're still a pretty small channel, honestly, and having you on board would be absolutely amazing. We'd love to have you join the community.
Yeah, totally. And we genuinely want to know what you think. What's blown your mind so far? Was it the reindeer's color-changing eyes, the tarsier's giant eyeballs, maybe the mantis shrimp? Let us know in the comments below. What was your biggest aha moment from this first half? We'd love to hear it.
All right, let's shift gears a bit. We've talked a lot about the physical hardware. The eyes, the ears, the weird body parts. Now let's dive into the software, maybe, the inner life.
Yeah.
We're moving from how they sense the world to what they're actually thinking. What kind of sophisticated strategies are they coming up with?
Tool use is the perfect bridge here, I think, because using a tool, even a simple one, often requires more than just instinct. It implies some level of planning, memory, understanding cause and effect.
Things we used to think only humans did,
Exactly. And it pops up in the most unexpected places.
like fish. I mean, when I think tool user, I think chimps, maybe crows, maybe otters. But our reading mentioned fish using tools
Mm.
in coral reefs.
Yep. Certain species of wrasse, for example, they've been observed picking up a clam or maybe a sea urchin in their mouth,
Okay.
then carrying it over to a specific rock, one they seem to favor, and then repeatedly smashing the shell against that rock, the anvil, until it cracks open so they can eat the inside.
Okay, but how do we know that's not just like a lucky accident? Why is that planning?
Well, a few reasons. First, they select the right kind of prey that needs cracking. Second, they transport it, sometimes a fair distance, to that specific rock. This suggests they have a memory of that location and its usefulness, a preferred anvil site.
The specific site is key.
Right. And then they perform a very deliberate multi-step action aimed at a specific goal. Getting the food out. It's not random bashing. It looks like a learned, goal-directed strategy based on remembering where the good tool is. Anticipatory planning.
Gotcha. Okay, the sea otter has a similar but way more adorable approach, right, with their little favorite rocks.
Totally adorable. Sea otters often have a favorite stone, one that's just the right size and shape for cracking open shellfish like clams or mussels.
And they keep it.
They do. They have this little pouch of loose skin under their forearms, like a built-in pocket. They'll often tuck their favorite cracking stone in there while they're swimming around or diving for more food.
Personal toolkit.
Exactly. It shows not just tool use, but tool selection, tool retention, maybe even tool refinement over time. They get good with their specific stone. It's individualized.
Okay, and then there are dolphins using sponges as
Yeah.
gloves.
Protective gear, basically. In some dolphin populations, particularly in Shark Bay, Australia, they've been seen tearing off pieces of marine sponge and fitting them over their rostrums, their beaks or snouts. They use these sponge gloves while foraging on the seafloor, probing the sand for hidden fish.
Why? What's it protecting them from?
Sharp bits of coral, maybe rocks, stinging critters hiding in the sand. It protects their sensitive snouts while they dig around. But here's the really profound part. It seems to be a learned behavior. It's taught primarily from mother to calf. It's passed down through generations within specific family lines.
So it's culture. A dolphin tool using culture.
That's exactly what researchers call it. Non-genetic cultural transmission of a tool-using technique in a marine mammal society. It's huge.
Wow, okay. And the octopus, the eight-armed genius, they use tools too, coconuts.
Yeah, the veined octopus is famous for this. They find discarded coconut shell halves on the seafloor. They check them out, seem to assess their suitability,
And then what?
and then they often carry them around, sometimes stacking two halves together, carrying them under their body, sometimes even stilt walking on two arms to keep the shells secure while the other 6 arms move them along.
Why are they carrying coconut shells around?
For shelter. They carry them, sometimes quite long distances, until they find a place they want to rest or hide. Then they pull the two halves around themselves, creating a portable, armored shelter, like a little mobile home.
They're planning ahead, anticipating needing shelter later.
Precisely. It's not just reacting to a threat right now, it's preparing for a potential future need for defense. That requires foresight.
Okay, foresight. Let's talk about the undisputed champions of planning and tool use, especially in our human-dominated world. Crows and ravens.
Oh yeah, the corvids. Absolute geniuses of adaptation and innovation. Crows, especially in urban areas, have come up with some amazing stuff.
Like the nut-cracking thing with cars.
The traffic light trick, it's brilliant. They find hard-shelled nuts, like walnuts, that they can't easily crack themselves. So what do? They fly over to a busy road intersection, and they drop the nut right in the path of oncoming car tires. They wait for a car to run it over and crack it open.
Okay, that's clever. But it's the next step that's really mind-blowing.
Exactly. They don't just drop it anywhere, anytime. They seem to learn the pattern. They often drop the nut, wait for the traffic light to turn red, stopping the cars.
And then they swoop down.
Then they safely hop down onto the crosswalk, usually, and retrieve their cracked nut when the cars are stopped. They've learned to use human traffic signals to their advantage. It shows an understanding of timing, risk, and cause and effect related to our infrastructure. They're weaponizing traffic lights.
Weaponizing traffic lights. Okay, ravens take that planning even further, right? Into like abstract thinking. Trade.
Yeah, our reading covered some fascinating experiments with ravens and trade. They were given objects that had no inherent value, like plastic bottle caps, that acted as tokens.
Okay, like a currency.
Basically, yeah. They quickly learned that they could exchange these tokens with a researcher later to get a tasty food reward.
Did they get it?
Oh, they got it. They started saving the tokens. Even more impressively, sometimes they were offered a choice. Take a small, immediate food reward right now, or take a token which they could exchange later for a much better, high-value treat.
And what did they choose?
They often chose the token. They resisted the immediate gratification of the small snack to save the currency for the bigger payoff later.
That's delayed gratification.
Yeah.
And understanding abstract value,
Yeah.
that's basically economics, isn't it?
It really forces you to reconsider what counts as complex cognition. Just the act of holding on to that token, remembering what it's worth, and planning to use it in the future, that shows a strong sense of future planning and self-control.
Okay. And scrub jays. They add another layer entirely, right? Like social paranoia.
Huh. Paranoia might be a good word for it. Scrub jays are masters of caching food, hiding it away for later, but they're also intensely aware of their social environment.
What do you mean?
When a scrub jay hides a food item, like an acorn, it pays very close attention to who might be watching it.
Other jays.
Yeah, potential thieves. If it notices that another jay, especially a dominant one, watched it hide the food, it will often wait until the watcher has left.
Yeah.
And then it will come back later, sometimes hours later, dig up the food, and secretly recache it somewhere else.
Get out. That's deception. That's like spy versus spy.
It's incredible social calculation. It implies they understand that the other bird saw them, that the other bird knows where the food is, and that the other bird might steal it. So they actively take steps to mislead the potential thief.
That's theory of mind, isn't it? Understanding that others have different knowledge or intentions.
That's exactly what researchers argue it demonstrates. The ability to attribute mental states like knowledge or desire to another individual and then act strategically based on that attribution. It's seriously sophisticated social intelligence in a bird brain.
Wow. Okay, and just to round off this section on planning and self-control, cuttlefish passed the marshmallow test.
Basically, yeah, a variation of it. Cuttlefish, which are mollusks related to octopuses, they showed they could wait for a better reward.
How'd it work?
They were given a choice. They could immediately eat a less preferred food item, like a piece of crab, or they could wait for a short period up to about 2 minutes, which is a long time for a cuttlefish, and then get their absolute favorite treat, like a live shrimp.
And they waited?
The ones that waited got the shrimp. They demonstrated self-control, resisting the immediate temptation to hold out for the better future outcome. It shows that complex cognitive abilities like patience and evaluating future rewards aren't just limited to us or even just vertebrates.
Okay, so we've gone from raw senses to physical bodies to tool use and planning, even social strategy. Now let's get into the really deep stuff. The emotional architecture, maybe, communication, consciousness, empathy.
Yeah, the evidence for rich emotional lives and complex communication in other animals is it's overwhelming when you start looking at the research.
Where do we even start? Elephants in Greece seems like a powerful example.
It really is. The way elephants respond to death in their group is incredibly moving and complex. Our reading documented this extensively.
They have rituals, right?
It looks very much like rituals. When a member of the family group dies, the others will often gather around the body. They'll touch the bones, sometimes gently stroking them with their trunks. They might stand silently for hours. They've even been seen returning to burial sites days, weeks, even years later to touch the bones again.
That implies such strong social bonds and long-term memory of individuals.
Absolutely. And it's not just about remembering the dead, it's about comforting the living. When an elephant is clearly distressed or grieving, maybe it lost its mother or calf, other elephants in the group will approach it.
And do what?
They offer comfort. They'll gently touch the distressed individual with their trunks, often around the face or mouth. They'll make these soft, low, rumbling sounds. It's clearly an intentional act of consolation, trying to soothe the other elephant.
That sounds like empathy. Actively recognizing distress and trying to alleviate it?
That's exactly what scientists argue it is. Strong evidence for active empathy, understanding the emotional state of another, and making an effort to help. And it's not just elephants.
Who else does this?
We see similar consolation behaviors across a surprising range of species. Chimpanzees will hug or groom individuals who've just lost a fight or seem upset. Wolves will nuzzle or lick stressed pack members. Even birds like ravens and parrots parrots have been seen preening distressed companions.
So this urge to comfort, to reduce stress in others, it seems like a really fundamental social glue in many animal societies, not just a human thing.
Not at all. It seems like a widespread strategy for maintaining social bonds and group cohesion.
Okay, from empathy to maybe the ultimate question, so, self-awareness, consciousness.
Yeah.
The mirror test is the classic way to look at this, right?
It's the most famous test, yeah. The idea is simple. You put a mark on an animal's body in a place they can only see in a mirror, like on their forehead or cheek. If, when they look in the mirror, they touch or investigate the mark on their own body, not just on the reflection, it suggests they understand that the reflection is them. They recognize themselves.
Which implies some level of self-awareness. And the big three usually pass this.
Historically, yes. Elephants, dolphins, and the great apes, chimpanzees, gorillas, orangutans have all shown convincing evidence of passing the mirror test. They see the mark in the mirror and try to touch it or rub it off themselves.
Okay, makes sense. Big brains, complex social lives. But then came the shockers, the ones that really threw a wrench in the works.
Oh, yeah. The discoveries that made everyone rethink what self-awareness requires. First, the magpie.
A bird, like the black and white bird that steals shiny things.
That's the one. A corvid, like crows and ravens. Magpies were shown to pass the mirror test. They saw the mark in the reflection and tried to scratch it off their own feathers below their beak.
Whoa. A bird brain is so different from a primate brain.
Totally different architecture. It suggested self-recognition could evolve convergently, using different neural pathways. But then came the really big shocker.
What could be more shocking than a bird?
A fish, specifically the cleaner wrasse.
The tiny little reef fish passed the mirror test. No way.
Yes way. Researchers put a small colored mark on the throats of cleaner wrasse. When these fish saw their reflection, they swam over to rocks or coral and scraped their throats against the surface, specifically where the mark was. They were trying to remove the mark they saw on themselves in the mirror.
That is unbelievable. A fish recognizing itself, what does that even mean for consciousness?
It means our assumptions were probably way too narrow. It suggests that the cognitive ability for self-recognition, this fundamental sense of me versus other, might be far more widespread and achievable with far simpler neural structures than we ever thought possible. Consciousness might be a much more flexible, adaptable, evolutionary solution.
Mind. Officially blown. Okay. If they're self-aware, even potentially, their communication must be pretty sophisticated too. You mentioned dolphins earlier. They have names.
They essentially do, yes. Signature whistles. Each dolphin develops its own unique, individually distinct whistle pattern early in life.
And other dolphins recognize it.
Oh, yeah. They use these signature whistles to call each other, to maintain contact, to identify individuals. It functions just like a name. And the social memory associated with these whistles is incredible. They can recognize the whistles of former companions even after being separated for decades.
Decades, wow. And they understand grammar too.
They seem to grasp grammar-like rules, at least in understanding human commands. Experiments have shown they understand that changing the order of words or gestures in a command sequence completely changes the meaning of the required action. That shows sensitivity to syntax, a key element of language.
Okay, now let's bring it back home.
Yeah.
Our dogs, best friends, they're obviously communicating with us, but how deep does it go?
Pretty deep, it seems, thanks to that long coevolution with humans. We know, for instance, that their brains process human speech in a way that's surprisingly similar to ours.
Uh-oh.
They seem to process the words themselves, the content, primarily in the left hemisphere of their brain, and the intonation, the emotional tone of voice, primarily in the right hemisphere, just like we do.
So they're getting both the what and the how
Yeah.
of what we say.
Exactly. And they're masters at reading our other cues, too, like pointing. Dogs understand human pointing gestures incredibly well, far better than even chimpanzees or wolves typically do.
Why is pointing special?
Because it's a really abstract, cooperative, communicative gesture. There's nothing inherent about an outstretched finger that means look over there. Dogs seem uniquely tuned in to interpret that human intention, likely because we've selected for that ability over thousands of years of domestication.
Okay, but the smelling emotions thing.
Yeah.
How exactly does a dog smell fear or happiness?
It boils down to chemistry. When we experience strong emotions, fear, stress, joy, excitement, our body chemistry changes. We release different hormones like adrenaline and cortisol when stressed, maybe oxytocin when happy.
And these have a smell.
They, or the compounds they break down into, are released in tiny, invisible amounts through our sweat and breath. They create a unique scent signature for that emotional state. Dogs, with their incredibly powerful noses, can detect these subtle chemical shifts.
So they're literally smelling our internal hormonal storm.
Pretty much, they don't need to see our face or hear our voice. They can smell our fear, our anxiety, our joy. It's a whole other layer of communication and connection happening right under our noses, so to speak. A kind of chemical empathy.
Wow, that bond is even deeper than I thought. Okay, what about rats laughing? That sounds made up.
It sounds crazy, but the research is solid. When rats are tickled, especially by a familiar human hand they trust, they emit these very high-frequency sounds around 50 kilohertz.
Way above our hearing range.
Totally silent to us. But when researchers record these sounds and slow them down, they sound remarkably like chirping or, well, laughter.
And it's linked to pleasure.
Definitely. It's strongly associated with play behavior and positive social interaction. They laugh more when playing with other rats or when being tickled in areas they seem to enjoy. If the rat is scared or stressed or tickled by something unfamiliar, they don't make the sound. It seems to be a genuine expression of social joy and trust.
Tiny rat giggles. Okay, I like that. Now, let's go back to the octopus. The ultimate visual display of an inner world. Octopus dreaming.
This is just stunning to watch if you ever get the chance to see footage. As an octopus sleeps, its skin goes through these incredible transformations.
The chromatophores, the color-changing cells.
Exactly. They fire in these complex, shifting patterns. The colors flash and ripple. The skin texture changes. It often looks exactly like the camouflage patterns they use when hiding, or the rapid color flashes they make when hunting prey.
So it looks like they're replaying scenes from their life, like dreaming.
That's the tantalizing interpretation. It really looks like we're watching their memories, their imagination, maybe their fears, literally projected onto their skin as they sleep. A living movie of their inner experience.
And given that most of their neurons aren't even in their head, but spread through their arms.
Right. Their body is their brain in many ways. So the skin becomes this incredible canvas displaying their neural activity during sleep. It's a visible record of their mind at work. Just breathtaking.
The body writing the mind. That's beautiful. Okay, let's quickly circle back to the Corvi's crows and their memory for faces. This is kind of creepy, too.
It is pretty intense. Crows have demonstrated an amazing ability to recognize individual human faces. They remember people who have been threatening or harmful to them and people who have been helpful or neutral.
And they remember for a long time.
For years. Even if the person changes clothes, wears a hat, maybe even a mask in some studies, they seem to lock on to specific facial features. They form grudges, essentially.
But the really wild part is they teach this to other crows.
That's the cultural transmission aspect. Research showed that crows that had never personally had a bad experience with someone wearing a specific dangerous mask would still react negatively, scolding, mobbing towards that mask.
Yeah.
They apparently learned it from watching the reactions of the original crows who did have the bad experience, or maybe through specific alarm calls associated with that face. New generations inherit the knowledge of who the enemy is without ever meeting them directly.
Passing grudges down through the family line. Wow, that's some serious social learning. Okay, finally, let's just touch on intelligence in places we really didn't expect it, like numerical or abstract concepts in tiny brains.
Right, because it's not all about social drama. The honeybee pops up again here. Astonishingly, bees seem capable of understanding the concept of zero.
Zero, like the number, nothingness.
As a quantity, yes. In experiments, they could learn to choose the image or stimulus that represented less than, and they correctly identified 0 as being less than 1, placing it at the correct end of a numerical sequence.
That's a huge cognitive leap.
Right.
Recognizing absence as having a numerical value.
It's a milestone that, until relatively recently, many thought was impossible for an insect brain. Shows incredible abstract reasoning.
Okay. And pigeons as art critics. Seriously.
Huh. Well, maybe not critics, but definitely discriminators. In categorization tasks, pigeons showed they could learn to tell the difference between paintings by different artists.
Like Monet versus Picasso.
Exactly. They weren't just memorizing specific paintings. They seemed to be picking up on general stylistic features like the brushstrokes, the color palette, the way light was used, and using those features to categorize new paintings by those artists correctly. They were recognizing abstract artistic styles.
Okay, bees understanding 0, pigeons appreciating impressionism. What else? Fish counting.
Even small fish show basic numerical abilities. Things like guppies or zebrafish can do what's called subitizing. That's rapidly recognizing small quantities without actually counting one by one.
How many can they recognize?
usually up to about 3 or 4, and they use this ability. For example, they'll consistently choose to swim towards a larger group, shoal of fish, rather than a smaller one, presumably because their safety in numbers. So they're making decisions based on a basic perception of quantity. It's ancient and vital for survival. Hashtag tag outro.
Wow. Okay. We have covered some serious ground tonight. I mean, from the pastel world of cats and dogs all the way to the completely unimaginable 16-channel hyperspectrum of the mantis shrimp.
Yeah, and thinking about elephants communicating through the earth with infrasound, or the chameleon's independently roving eyes calculating depth.
Or the sheer emotional depth we talked about, the grieving elephants being comforted, the scrub jay's strategic deception, the self-recognition in a tiny fish.
I think the core thing, the big realization we hope you walk away with tonight is just how universal intelligence and complex emotions seem to be. They aren't exclusive human properties.
Right, they're like design solutions.
Exactly. They're nature's solutions to the problems of survival, communication, and navigating a complex world. And they pop up everywhere, taking these incredibly diverse and surprising forms, perfectly adapted to local needs.
Whether that means using your job on a sonar, or needing 3 eyelids, or having a brain capable of understanding the concept of zero.
Yeah. It just shows we're far more connected, far more interwoven with the rest of the natural world, and perhaps far less unique than we often tend to think.
This whole deep dive really has been about trying to crack open our own perspective, hasn't it?
Yeah.
Trying to imagine what the world looks like, sounds like, feels like through entirely different senses, different minds, realizing just how narrow our own little sensory window is.
Mm-hmm. Which brings us, I guess, to that final thought, something to maybe mull over as you drift off.
Okay, lay it on us.
We talked about how octopuses seem to write their inner life, maybe even their dreams, onto their skin with those shifting colors, a visible record.
Yeah, beautiful and mind-bending.
And we also know from their twitching paws and muffled yips that our own dogs almost certainly dream, likely about us, about walks, about chasing squirrels, reliving their experiences.
Okay.
So the final question is, what other records are out there? What visible or maybe silent records of connection, of shared experience, maybe even love or collective memory? What signals are constantly happening all around us right now?
That we're just completely missing.
Exactly. Simply because we don't have the right senses. We don't have the 16 color receptors or the infrasound hearing or the ability to see polarized light or smell fear across a room. What stories are being told that we just can't perceive?
Whoa, okay. That's definitely something to chew on. What are we blind and deaf to?
Something to ponder. Thanks so much for joining us tonight for this deep dive into the often hidden, always fascinating minds of the animal kingdom.
Yeah. Thanks, everyone. We'll catch you next time. Sleep well.